Hello everyone, this is Divya. In this session, we are going to discuss about gas law and its applications. In this session, we are going to discuss about introduction to gas law, mathematical formula of gas law, and application and limitations on gas law. Let's discuss introduction to gas law. Gas law is a fundamental principle in physics that relates the electric flux through a closed surface to the charge enclosed by that surface. It is a powerful tool for calculating electrical fields in symmetric situations. Gauss law is based on the concept of electric flux, which is amount of electric field passing through a given area. Next is mathematical formulation of Gauss law. Gauss law can be expressed as psi E dot dA is equals to Q divided by X plus naught, where E is the electrical field. Psi is the symbol for the electrical flux, dA is the differential area element, and Q is the total charge enclosed by the surface, and epsilon naught is the permittivity of the free space. The left-hand side of the equation represents the electrical flux through a closed surface, while the right-hand side represents the total charge enclosed by that surface. When Gauss law is the consequences of the divergence theorem, which relates a surface integral of a volume integral. Applications of Gauss law. In different fields, we are using the Gauss law in that symmetric charge distributions is one of the application. Gauss law is particularly useful for calculating the electrical fields in situations with high symmetry, such as uniformly charged sphere or a charged infinite plane. By choosing a Gaussian surface that matches the symmetry of the charge distribution, the electrical field can be easily calculated using Gauss law. This simplifies the calculation compared to using Coulomb's law is directly. The application of Gauss law here it is the determination of the electrical field. In the spherical symmetry, we are using the formula E is equals to Q divided by 4 pi epsilon naught into r square. In the cylindrical symmetry, we are using E is equals to lambda divided by 2 pi epsilon naught into r. And in the planar symmetry, we are using E is equals to sigma divided by 2 epsilon naught. And the next is application of gas line conductors and insulators. Gas law can also be used to analyze the behavior of electrical fields inside conductors and insulators. Inside a conductor at electrostatic equilibrium, the electric field is zero and charges reside on the surface of the conductor. For insulators, gas law can be used to analyze the electrical field inside the material at the interfaces. Application of gas law in the flux through non-closed surfaces. Gas law can be applied to calculate the electrical flux through non-closed surfaces by considering the net charge enclosed by the surface. This allows for the calculation of electrical fields in more complex geometries such as cylindrical and spherical shells. Gas law can be expressed in the electrical field in a differential form. We are using the formula delta dot E is equals to rho divided by x plus naught. In the integral form, integration of E dot n cap into dA is equals to Q enclosed divided by x plus naught. Here dA is nothing but the flux that passes through a closed surface is proportional to the charge enclosed therein. And the choice of the Gaussian surface is crucial in determining the electric field using the Gauss law. Gauss law and Maxwell equations. Gauss law is one of the four Maxwell equations which form the foundation of classical electromagnetism. This shows the difference or the relation of the Gauss law and the Maxwell equations, which together with the Gauss law of magnetism, Faraday's law of induction, and Ampere law with Maxwell correction. These equations describe how electric and magnetic fields are interact. Maxwell equations are essential for understanding the behavior of electromagnetic waves and the propagation of the light. Here some equations will be shown here, that is phi is directly proportional to enclosed charge enclosure, that is Gauss law that is electrical flux is directly proportional to charge enclosure, and electric flux is equals to psi into E dot ds is equals to Q enclosure with explanade. Gas law in differential form. Gas law can also express it in differential form using the divergence of the electrical field. Delta dot E is equals to rho divided by explanade, where where delta is the divergence operator and rho is the charge density. This form of gas law relates the behavior of the electrical field at a point to the charge density at the point. The differential form is useful for analyzing the electrical fields in continuous charge distributions. Gas law and electric flux. The relation between gas law and electric flux. The electric flux is a crucial concept in the gas law, representing the flow of electric field through a surface. The electric flux through a closed surface is proportional to the total charge enclosed by that surface. By calculating the electric flux, one can determine the amount of electric field passing through a given area. And the next is gas law in modern physics. Gas law plays a significant role in the modern physics, particularly in the study of electromagnetism and the quantum mechanics. It is used in various applications, including the design of electronic devices, electromagnetic wave propagation, and particle physics. Understanding gas law is essential for engineers, physicists, and research working in the fields related to electromagnetism. And finally, we came to conclusion part of this session. Gas law is a powerful tool for calculating electric fields in the symmetric situations and understanding the behavior of electrical charges. It is based on the concept of electric flux and related to flux through a closed surface to the charge enclosed by the surface. By applying gas law, physicists and engineers can analyze and predict the behavior of electric fields in the various scenarios. Thank you.